I want to begin with something that happened to me in the autumn of 1947. I was 23 years old, a young British mathematician who had just crossed the Atlantic to work at Cornell University with Hans Bethe. I had arrived full of confidence, perhaps too much of it, and I was about to have that confidence very usefully dismantled. One afternoon a man knocked on the door of my office. He walked in sideways as though he wasn't entirely sure the room deserved him, and he started talking. He spoke the way other people breathe, continuously, without apparent effort, and with the sense that stopping would be unnatural. His name was Richard Feynman, and within 10 minutes of meeting him I realized he understood something about light that I did not. That is what I want to talk to you about today. Not Feynman exactly, though he will appear again shortly. I want to talk about light, about what it actually is, about how it travels, and about the very strange fact, one of the strangest in all of physics, that from the photon's own point of view, it does not travel at all. Let me say that again, because I think it is worth sitting with for a moment. A photon, a particle of light, leaves the surface of the sun. 8 minutes later, by our reckoning, it arrives at your eye on a summer afternoon. It has crossed 150 million kilometers of empty space. And yet, if you could ask that photon what the journey was like, the honest answer, the answer demanded by Einstein's theory of special relativity, is that there was no journey. No distance was covered. No time passed. The sun and your eye for that photon were the same place at the same moment. This is not a paradox. It is not a trick of language. It is what the mathematics insists upon, and it is one of the most profound things we know about the universe. Now, I am aware that this sounds like the sort of statement that belongs in a philosophy lecture, not a physics one. I have spent my career trying to dissolve that boundary. Physics done carefully and honestly is philosophy. And the question of how light travels, or whether it travels at all, sits exactly at that boundary. To understand it, we have to go back. We have to go back well before Feynman, well before Einstein, back to a man working in Scotland in the 1860s by the name of James Clerk Maxwell. Maxwell was, in my personal estimation, the greatest physicist of the 19th century, greater than his contemporaries appreciated, even greater in some ways than Einstein appreciated, because Einstein's special relativity is hiding in plain sight inside Maxwell's equations, if only you know where to look. Maxwell unified electricity and magnetism. Before Maxwell, these were two separate forces. After Maxwell, they were two faces of the same thing, the electromagnetic field. And in the course of that unification, Maxwell made a calculation. He asked, if I disturb this field, how fast does the disturbance propagate? The answer came out at approximately 300,000 kilometers per second. He recognized immediately that this was the speed of light. He wrote in a letter to a colleague words to the effect that we can scarcely avoid the inference that light consists in the transverse undulations of the same medium which is the cause of electric and magnetic phenomena. What Maxwell discovered, in other words, is that light is not a thing being thrown through space. Light is a disturbance in a field. It is the field itself oscillating, the electric component and the magnetic component, each driving the other forward, leapfrogging through space in a self-sustaining wave. There is no projectile, there is no substance, there is only a pattern propagating. This is already strange, but it gets stranger. Maxwell's equations have a peculiarity that troubled physicists for 40 years after his death. They predict a specific speed for light, that 300,000 kilometers per second, but they do not say speed relative to what? Every other speed we knew about was relative. The speed of a cannonball is measured relative to the ground. The speed of a river current is measured relative to the riverbank. Speed, as Newton understood it, always meant speed in relation to something. But Maxwell's equations gave a fixed speed with no reference point. The obvious solution was to propose a medium. If light was a wave, there must be something for it to wave through, just as sound waves travel through air and ocean waves travel through water. They called this medium the ether, and they set out to detect it. The most elegant of these attempts was performed in 1887 by two Americans, Albert Michelson and Edward Morley, in a basement in Cleveland, Ohio. They built an instrument of extraordinary precision, an interferometer, designed to detect the difference in the speed of light depending on whether it was traveling with or against the Earth's motion through the ether. The Earth moves at roughly 30 kilometers per second in its orbit around the Sun. If the ether existed, there should be a detectable shift They found nothing, no shift, no ether. The experiment was so carefully done and the null results so unambiguous that it was simply impossible to explain away. But it took another 18 years and a young patent clerk in Bern before someone drew the correct conclusion. Einstein's conclusion was this: there is no ether because none is needed. The speed of light is absolute, not relative to any medium, not relative to any observer, but fixed and constant for everyone, everywhere, regardless of their motion. If you are standing still and I am moving toward you at half the speed of light, and we both measure the speed of the same beam of light, we will both get the same answer. Not different answers, the same answer. This seems impossible. It contradicts every intuition we have about relative motion. And yet it is true. The reason it is true is that space and time are not what we think they are. They are not fixed and absolute. They flex and adjust, so that the speed of light remains constant. Time slows down, distances contract, the universe rearranges itself silently, invisibly, to preserve the constancy of light. And here we arrive at the strange truth I mentioned at the beginning. Einstein's relativity tells us that as you move faster, time for you slows down relative to an observer who is stationary. This is not an illusion. It has been measured very precisely using atomic clocks on aeroplanes. A clock that flies around the world runs slightly behind a clock that stays on the ground. The effect is tiny at the speeds of aeroplanes, but it is real. As you approach the speed of light, the effect becomes enormous. For something moving at 99% of the speed of light, time would be passing roughly 7 times more slowly than for a stationary observer. Now push that reasoning to its limit. What happens at the speed of light itself? The mathematics gives a definite answer. At the speed of light, time dilation becomes infinite. Time does not slow down, it stops. A clock moving at the speed of light would not tick at all. And length contraction, the companion effect, also becomes infinite. The entire distance between the source and the destination would contract to zero. This is what I mean when I say the photon does not travel. For the photon there is no distance and there is no duration. The moment of emission and the moment of absorption are, from the photon's reference frame, the same moment. A photon that left a galaxy 2 billion light-years away and arrived at a telescope last Tuesday did not experience 2 billion years of travel. It experienced nothing. It existed at emission and at absorption, and there was for it nothing in between. Now I should be careful here. Physicists are sometimes queasy about the phrase the photon's reference frame, because a proper inertial reference frame, in the sense Einstein defined it, cannot be constructed for something traveling at exactly the speed of light. The mathematics becomes singular, it divides by zero in a sense. So when I say the photon experiences no time, I mean we should understand this as a limiting statement. As you approach the speed of light, the experienced time approaches zero, and the limit of that process at the speed of light is zero itself. The destination is that there is no journey. This is the reality check of my title. We say light travels. We say it moves at 300,000 kilometers per second. And in our reference frame, from our point of view, all of that is entirely correct and useful. But the deeper description, the description that does not privilege any particular observer, tells a different story. Light connects two events in space-time. It is a relationship between them. The question of what happened in between is, in the strictest sense, not a question that has a physical answer. Let me now bring in Richard Feynman again, because he contributed something essential to this picture. By the late 1940s, we had Maxwell's classical theory of light, and we had Einstein's relativity, and these two fit together beautifully. But we also had quantum mechanics, and quantum mechanics had a very different notion of what light was. Light was not only a wave, it was also a particle, the photon, and photons were quantum objects subject to uncertainty, superposition, and all the other strangeness of the quantum world. Reconciling the quantum theory of the electron with Maxwell's classical theory of light had been a problem of extraordinary difficulty. The early attempts were plagued by infinities. When you tried to calculate the energy of an electron interacting with its own electromagnetic field, the answer came out infinite. This was clearly nonsense, but nobody could see how to remove the infinity without throwing out the physics along with it. Feynman found a way, or rather, 3 people found a way at almost exactly the same time. Feynman in America, Julian Schwinger also in America, and Shinichiro Tominaga in Japan. They each developed a method for dealing with these infinities through a procedure called renormalization, and they each arrived at the same physical theory, which we now call quantum electrodynamics, or QED. My own contribution, and I describe it with appropriate modesty, was to show that all three methods were mathematically equivalent. This was not entirely straightforward. Feynman's approach, with his extraordinary diagrams, looked nothing like the operator algebra of Schwinger and Tominaga. It took me the better part of a year, and a very long bus journey across the American Southwest to work out the proof, but the proof existed and the theory was unified. What QED tells us about light is something still stranger than what I have described so far. In QED, a photon traveling from one place to another does not simply travel in a straight line. It takes in a very precise quantum mechanical sense all paths simultaneously. It goes by the direct route, it goes around the long way, it loops back on itself. It does all of these things at once, and these alternative paths interfere with each other, and out of that interference emerges the appearance of a straight-line trajectory. This is the path integral formulation, Feynman's great gift to physics. The photon explores all possible paths through space-time, and the probability of it arriving at any given destination is determined by the sum of all those explorations. Straight-line travel is what emerges when most of the paths interfere destructively and cancel out, leaving only the paths close to the classical trajectory to reinforce each other. There is something wonderful about this picture if you are prepared to sit with the strangeness of it. The photon does not know in advance which way to go. It does not follow a predetermined path. It feels out the entire landscape of possibility and arrives where the geometry of space-time directs it. The universe at the quantum level is not a machine following a script. It is something more like a vast computation or a vast improvisation, in which the final notes are determined by the entire structure of what came before. I have been asked over the years whether this means light has some kind of experience, whether there is something it is like to be a photon. I find this question genuinely interesting, and I have never been willing to dismiss it as simply confused. The photon is a quantum object. It has no definite trajectory until it is measured. It exists in superposition. It has, in the relativistic sense, no internal clock ticking away the duration of its journey. These are very strange properties. Whether they add up to something we would call experience, I honestly do not know. I suspect no one does. What I do know is that they add up to something very different from the common picture of light as a stream of tiny bullets fired through space. The photon is more like a question asked by the universe to which the geometry of space-time supplies the answer. Now let me come back to something more historical, because I think the history of these ideas is inseparable from understanding them properly. When Maxwell published his equations in 1865, almost nobody understood their significance. Maxwell himself did not fully grasp the implications for relativity, which would not be formulated for another 40 years. The British physicists of the era, trained in the mechanical traditions of Newton, wanted to understand the electromagnetic field as a kind of stress in a medium, a mechanical model, something you could in principle build in a workshop. Maxwell's equations resisted that. They described the field directly without underlying mechanism. This made them profoundly uncomfortable to the Victorian scientific mind. Heinrich Hertz, who confirmed Maxwell's predictions experimentally in 1887 and produced radio waves for the first time, said something that has always struck me as exactly right. He said that Maxwell's theory is Maxwell's equations, not the mechanical models, not the ether, not any underlying picture, just the equations themselves, and that the equations taken on their own terms contain all of the physics. This is a philosophical position as much as a scientific one. It says that the equations are reality, or at least that the equations are as close to reality as we can get. The question of what is really happening underneath, what the field really is, what the photon really is, these questions may not have answers that we can form into pictures. They may only have answers that we can write down in mathematics. I find this both humbling and exhilarating. Humbling because it means our intuitions formed over millions of years of evolution to deal with rocks and rivers and other animals are simply not equipped to handle the deep structure of the universe. Exhilarating because the mathematics works. The predictions of QED are the most precisely confirmed in all of physics. The anomalous magnetic moment of the electron, a tiny correction to the electron's magnetic properties arising from its interaction with the quantum electromagnetic field, has been calculated and measured to more than 10 significant figures, and theory and experiment agree to that extraordinary precision. The universe is not required to be comprehensible to us, but it is, and the language in which it chooses to be comprehensible is mathematics. There is one more thing I want to say, and it is perhaps the most important. Light is not incidental to the structure of the universe. Light is not something that happens to exist like rocks or trees. The universe, in the relativistic sense, is built around the speed of light. The speed of light is not a property of light, it is a property of space-time itself. It is the conversion factor between space and time, the fundamental constant that tells you how much time 1 meter is equivalent to and how much space 1 second corresponds to. If you removed all the photons from the universe, the speed of light would still be embedded in the geometry of space-time. This means that when we try to understand light, we are trying to understand something that is constitutive of the universe at the deepest level. We are not studying a phenomenon, we are studying in a very real sense the skeleton of reality. Maxwell's equations tell us that the electromagnetic field is self-sustaining, that an oscillating electric field generates a magnetic field, and an oscillating magnetic field generates an electric field, and together they carry each other forward through space, with no medium and no mechanism required beyond the field itself. Einstein's relativity tells us that the speed at which this propagation occurs is not a speed in the ordinary sense, but a structural feature of space and time. And Feynman's QED tells us that the photon carrying this field from one place to another does not travel in any classical sense, it explores simultaneously the entire fabric of possibility. Put these things together and you have a picture of light that is frankly astounding. Light travels, and it does not travel. It connects 2 points in space-time, across which for it there is no distance. It follows every path at once. It carries no clock, feels no duration, and arrives not at the end of a journey, but at the completion of a relationship between an emission event and an absorption event, mediated by a field that is as fundamental as space-time itself. I began my career as a mathematician who came to physics. I spent the better part of 7 decades at the Institute for Advanced Study in Princeton, working on quantum field theory, statistical mechanics, nuclear engineering, and half a dozen other things that struck me as interesting. I have never lost the mathematician's conviction that the deepest truths have a kind of elegance, not prettiness, but economy. The right description does not require more machinery than is needed, and by that standard light is about as elegant as anything in physics. It is the simplest thing in the universe that is also, upon examination, one of the most strange. It obeys equations of classical beauty, and those equations, when subjected to the full force of quantum mechanics and relativity, reveal a structure of inexhaustible depth. The title of this talk promises a reality check. Here it is. The reality is that light does not travel the way you think it does. The reality is that the photon has no experience of its journey because there is no journey to have. The reality is that the universe is structured around the constancy of light speed in a way that makes space and time themselves mutable. And the reality is that all of this has been confirmed repeatedly and precisely by experiment. The common picture, light as a beam racing through darkness, covering distance at a steady speed, is useful. It is true in the practical sense that Newton's laws are true, approximately right in the situations we normally encounter. But it is not the deepest truth available to us. The deeper truth is stranger. And in my experience, the stranger the truth, the more reliably it is true. Thank you.